An object or system that is stationary and experiences no acceleration is said to be in static equilibrium with its environment. In this condition, the object or system experiences a zero net force, and the system remains either at rest or moving at a constant velocity in accordance with Newton's first law. In this video, we will look at an example of a static system and analyze how Newton's laws are applied to the forces acting on it. Consider a traffic light that is suspended by cables as shown in the diagram. The traffic light is static with its environment, so it's not moving in any direction. The weight of the traffic light is 100 newtons, so it has a mass of about 10 kilograms. As an engineer, you might be interested to know what forces are acting on the cables so that you can pick the cables with the right strength to support the traffic light. So let's work out the forces on this cable. The first thing to determine is how many parts of interest are there in the system. What we see is that there are 3 cables, which we'll call cables 1, 2, and 3. And of course, there's the traffic light. We notice that cables 1 and 2 are at some angle to the horizontal beam that it is attached to. So any forces acting on these cables will have horizontal and vertical components. We will then need to define a coordinate system. So let's define the upward direction as positive y and the direction to the right as positive x. Let's start our force analysis by looking at the traffic light. Because it has mass, it has weight pointing directly downwards due to gravity. The magnitude of this weight is 100 newtons. We see that the traffic light is attached to cable 3, which is orientated vertically. According to Newton's second law, if there is no net acceleration, then there is no net force. So cable 3 must pull on the traffic light with the same force as its weight to balance the forces out and the traffic light stays stationary. In physics, a pulling force that is applied to an object like a cable, a cord, or string is called a tension. So we will label this force as T3, being the tension on cable 3 due to the traffic light. At the upper end of cable 3, it is pulling on cables 1 and 2. So cable 3 pulls up on the traffic light but pulls down on cables 1 and 2. The upper pulling force is a reaction to the lower pulling force as determined by Newton's third law. Since cables 1 and 2 are pulling on cable 3, then there is tension in them directed along the length of the cables. We'll call these tensions T1 and T2. As cable 1 is angled at 37 degrees below the horizontal, the tension in cable 1 can be resolved into a horizontal component which we'll call T1x and a vertical component which we'll call T1y. Similarly, the tension in cable 2 will have a horizontal and vertical component as well, which we'll label as T2x and T2y. Because the system is in static equilibrium, all of the forces along the horizontal direction must add up to 0, and all of the forces along the vertical direction must also add up to 0. Let's first look at the x direction. Along the x direction, we have T2x pointing to the right, which we've defined as being the positive direction, and we have T1x pointing to the left, which is in the negative direction. So the vector sum of the forces along the x direction is given by T2x minus T1x is equal to 0, or T2x must be equal to T1x. Since T2x is a horizontal component of T2, it can be written as T2 cos of 53 degrees. Similarly, T1x is a horizontal component of T1, so it can be written as T1 cos of 37 degrees. Along the vertical, we have T1y and T2y pointing upwards in a positive y direction and T3 pointing downwards in a negative y direction. So the sum of the forces in the cable junction along the y direction gives T1y plus T2y minus T3 to equal 0, or T1y plus T2y equals T3. T1y and T2y can be written in terms of the cable tensions T1 and T2 as T1 sine of 37 degrees being the vertical component of T1 and T2 sine of 53 degrees being the vertical component of T2. And finally, for the traffic light, we have T3 pointing up and the weight pointing down, the vector sum of the two being equal to 0. So T3 must be equal to W. So we're now left with three equations and three unknown variables, t1, t2 and t3. But t3 is equal to the weight of the traffic light, which is known and is equal to 100 newtons. So there's really only two unknown variables, t1 and t2. Given that both unknown variables appear in the two remaining equations, we can use the simultaneous equations by substitution method to solve for them. They won't be solved here in this video, and it's left to you to try to solve as practice in the quiz. But if you want a refresher on simultaneous equations, click on the link in the video.